Yes, so potentiometer will be used to measure EMF of a cell, and sometimes it will be used to compare EMF of two different cells, and it is also used to measure internal resistance of a given cell, that is measure internal resistance. So these are the three use cases of potentiometer, and for measuring the voltage we already have a device called voltmeter, right? So still we have another device here that is called potentiometer. So we'll also see which one is better and why, which one is better and why. So we'll see that later. Now let's see how this device looks like, the circuit diagram for this. So here you have, it is somewhat similar to meter bridge. It is based on the same principle, that is principle of Wheatstone bridge. So somewhat it will be similar to that, but not exactly same as meter bridge, right? So again, there is this A to B, that is one long wire. This long wire is not 1 meter. So that's why this is not meter bridge, right? Now, some other circuit elements are here. That is, for example, let's say this is that cell that will, or the battery that will drive this circuit, whose EMF is E and internal resistance is R. And let's say here there is a key, that is to close the circuit and to open the circuit. Close the circuit means when the current starts flowing in the circuit. Then we have a variable resistance here, the resistance which can change. Such device is called, or it is shown like this. If I show only that zigzag line, that is a resistance, which is a fixed resistance. When I draw an arrow on that, it becomes, or it is shorthand for a device called rheostat, which can change its resistance. There will be a knob, and through that knob, or there will be a slider. If you move it, the resistance of that device, resistance in the circuit, changes, right? Then the next part of this circuit starts from here. In this part, there is a cell here, again, whose EMF suppose is E, and then it is connected through a jockey and galvanometer to this wire. So again, this jockey will be used to slide the wire connecting galvanometer on that wire AB. This wire AB, we have drawn it like this, but if you see in your lab, it will be like this. It is more than 1 meter of length. So to accommodate more length, it will be in this shape, right? It will be it will be taking so many turns so that the length of the wire is more than 1 meters. Okay, this cell, the cell in the green with capital E, this is the unknown resistance, sorry, unknown EMF. This is what we have to calculate, or we have to find out, investigate. Right. Now this part which you see here, this is called the primary circuit, and this part which you see here, this is called the secondary circuit. So this entire thing is divided into two segments, that is primary circuit and the secondary circuit. In the secondary circuit, there is the cell whose EMF we have to calculate. Other devices, I think you already know, that is this J stands for jockey. Jockey is a slider which will move, and this K is key. This is the K, which is actually a key. The resistance, the potentiometer wire, that is R, is resistance, that is total resistance of wire AB. This wire AB is also called potentiometer wire, right? So that is potentiometer wire, and let rho be the resistivity of that wire. So that is the resistivity of the wire, and RH, as we have already seen, that is the rheostat, variable resistance given by the rheostat. Now, what does this do? This variable resistance is responsible for controlling the current through wire AB. So what does it do? It controls, because if you increase the resistance, current decreases. You decrease the resistance, current increases. So it controls the current through the wire AB. The current through wire AB. That is the purpose of this variable resistance. Right? So one terminal of, as you can see here, it consists of this long wire AB of length L, and it will be almost 6 meters of length. Not necessarily, but it will be approximately 6 meters of length. That is your AB. So it consists of that long resistive wire of length L. So instead of taking this whole number, just take it as L. It will be around 6 to 10 meters. Sometimes it will be even 10 meters. So because it is 10 meter and that is a long length, so that's why it is in this shape which you are seeing here. And a battery of unknown voltage, known voltage, this one is known. We know this, right? And that is the driving battery. And internal resistance R, this is the driving battery or the supplier battery. We can say this is the driver cell or the supplier battery. So this supplies the current. Now connection of these uh, things which we have seen here, that is the rheostat, wire, and the cell, that actually forms the primary circuit. Another one terminal of another cell, as you can see here, this is the another unknown cell. Of this, one terminal is connected to one end of the main circuit, and the other terminal at any point on the resistive wire, the wire which has resistance through a galvanometer G. Now this forms the secondary circuit, as you have seen here. Now there are few points which we should remember in this. So let's discuss those few important points. So what are these important points? These are: first, the specific resistance or the resistivity of potentiometer wire must be high, but its temperature coefficient must be low. Rho, that is the resistivity of AB, should be high, but temperature coefficient means alpha. alpha of AB must be low. So we should know what is alpha, and the resistivity is resistance per unit length per unit area, and alpha, that is temperature coefficient. It actually gives us an idea about how much increase in resistance will be there per unit temperature, sorry, per unit current which flows through this. So that is about the alpha. So obviously its resistance must not change much with change in temperature. So that's why that is for the ideal situation. Second point is all higher potential points, that is the terminals of primary and secondary circuits, must be connected together at point A, and the lower potential points must be connected to point B or jockey. The here, if you see here, right, the higher potential, that is plus, and this plus, they are connected to A, and the lower potential is connected to, you can see here, B or through the jockey. So to summarize that, and this will be in your lab as well, so that's why it is important, higher potential or positive of both cell connected to A, and negative of both cell connected to B, and I'll just write J. I hope you understand that that is jockey. Now the unknown potential which we are going to find, that must be greater than the value of the known potential must be greater than the value of unknown potential. So V known, or we have actually given it two different names, that is small e and capital E. So this small e value must be greater than capital E value. This is known and this is unknown, and that's why that is called driving or driver battery, because it has higher potential, so it will drive the direction of the current. Now there is something called potential gradient, and that must remain constant. We'll see what is that potential gradient. So potential gradient must be constant, potential gradient of the wire. And for this, the current in the primary circuit must remain constant. The current in primary circuit must be constant. Right? So the current in the primary circuit must remain constant, and the jockey must not be slided in contact with the wire. This is something which you have to take care during your experiment. Jockey must not be slided. So you should actually pick it up and put at different points. Don't slide it, don't rub it. So we'll explain that why this is required, and this is an important tip from practical point of view, right? And the diameter of the potential wire must be uniform. That is the last point. That is the, or I can simply say wire AB must be of uniform thickness. Because if that is not there, the resistance will change, because resistance changes with diameter or thickness. More thickness, less resistance, less thickness, more resistance. So, and if resistance will change, the current will also change. And as we have seen in the fourth point, current has to remain constant. So these are the 5 points which we have to take care. Now we'll see what actually is potential gradient, because we have introduced that term here, right? So let's see what is potential gradient. Gradient actually means change, right? So the potential difference, this we represent it as x. The potential difference, or when current flows, the potential decreases. So we can say fall in potential per unit length of wire is called potential gradient. So this potential gradient x is nothing but fall in potential per unit change in per unit length of wire. So there is a wire. When current flows in this, say I current, and this wire has some resistance R. These are the 2 points, say A and B, whose length is say L, and this VAB is equals to say V. Then this potential gradient x will be equals to this VAB divided by length. This is potential gradient, or the rate of change of potential per unit length. So if we are talking about this is nothing but resistance of AB section divided by length of that segment. That is what potential gradient is, or simply R by L. So this X is equals to, you can say V by L, or this is equals to some I into R. Sorry, there will be I here as well. I into R divided by L. That is the potential gradient. And this R is equals to rho L over A. So this can also be written as I. Instead of R, I can write rho L divided by L into A, so that these two cancel and I get I into rho divided by A. So even this is potential gradient, even this is potential gradient. Correct. Now uh, if we see our circuit clearly, the potential of 2 points, that is current, in this, if I take this, right, so the current which I have to find, that current is nothing but E divided by the resistance R and the resistance RH and the internal resistance R, right? So what is R? R is the R is actually the resistance per unit length, the total resistance of the wire. This is R, right? This is I. So now when I say X, so X is equals to I. So I means E divided by R plus RH plus R into R by L. So this we are deriving from this one, the basic definition, that is IR divided by L. So I is, you should be clear about this. How did we get I is equals to E divided by R plus RH? So go back to the circuit diagram, and there you can see that in the primary circuit, E is the driving E, that is small e, that is the driving EMF, and the total resistance of that is the resistance of AB. Resistance of AB is capital R, then the RH, and then the internal resistance of the cell. So from there we got this, that the potential gradient or different forms of potential gradient. So these are the different forms which you can see here. So now let's move to the next part. So we have already seen that potential gradient. If we now study this potential gradient in little detail, so we know what is potential gradient, but it depends on few things. That is this gradient x, the gradient x or the potential gradient x. It is directly dependent on the resistance per unit length on R by L, that is resistance per unit length of potentiometer wire, and it will be also directly related to the radius of the potentiometer wire, that is the area of cross section. So this is our first thing on which it depends. It also depends on area of cross section, because if that changes, R by L will also change. So area of cross section or the radius, the specific resistance of the material of the potentiometer wire, that is there in our formula itself here, the specific resistance. Right, and the current flowing through the potentiometer wire, so even that we have seen, it also depends on the current. Now these are the things on which this potential gradient depends, and that's why we have actually listed them in the important points which we have to take care, right? And it also indirectly depends on, that is inversely or so what are the factors on which it indirectly depends? That is EMF of the battery in the primary circuit. I'll say simply EMF of driver, battery or cell, right? Next, the resistance of the rheostat, that is simply RH. So those are the factors also which indirectly affect the potential gradient. Now, when the potential difference V is constant, if potential difference, this is, if that is constant between any 2 points, then potential gradient along say one section will be equals to V by, say that section will have length L1, and x2 will be say V divided by L2, then x1 by x2 will be equals to L2 by L1. That is an important point again. Now if two different wires are connected in series to a potentiometer wire, then again the potential difference will change. And if the length of the potentiometer wire and the potential difference across its ends are kept constant, and its diameter is changed, then the potential gradient remains unchanged, and the value of x does not change with any change affected in the secondary circuit. So this we have to, these are the points which we have to note or take care. Now let's see how this device works. That is the working of this device. Now suppose the jockey which we have seen is made to touch a point, say J, and then potential difference between A and J is measured or calculated, right? So suppose this is the wire AB, and the jockey J is suppose made to touch at this point, that is J. And now suppose this length is actually given by this small l, and we know the potential gradient of this AB is x, right? So x is potential difference per unit length and L is the length. So x into L will give us the total potential difference between A and J. So suppose this jockey is made to touch this point J, and then potential difference across A and J, that is V A J, will be equals to x into L. From this diagram we got this, right? Where A and B are the endpoints, J is the point where you have touched it. At this length, two potential differences are obtained. That is, at L, there will be two potential differences. This x into L is our calculation. So the first potential difference V will be due to E, and the second will be capital E, that is due to unknown cell. Right. So these are the two potential differences. Now there are two things, that is, if V is greater than E, that is the driving voltage is greater than the unknown EMF. If that is the case, then current will flow in galvanometer circuit in one direction. If V is greater than E, then current in G in one direction. Suppose we show it like this, right? This is how the galvanometer will show. And if V is less than E, then the current will be in some opposite direction, in the opposite direction. So let us show that by this. Right. So we have to find this point where the current changes its direction. So that point is actually the point where the current is changing direction. That means where the voltage of primary circuit, that is primary cell, or not primary cell, the driver cell, was anyways greater than, but this is the point where this changes. That is the value of V and E. If you compare them, the V is greater than E changes to V less than E. So that means at V equals to E, that is, if the primary circuit voltage is equals to E, then there should be no deflection in the galvanometer. So this shows that there is no current in galvanometer when V is equals to E, right? And what is V? V is the potential difference in the primary circuit, that is between A and B. Now this is called the balance situation, when there is no current in this galvanometer, but the entire current is there in the primary circuit, right? So in this balanced condition, where the current in galvanometer is 0, we say that this, or we conclude that this E will be equals to XL, the total potential difference. Why you understood, right? Because in this, between say A and J, there is a potential difference and there is a cell here, and even due to that cell there is no current in this segment. That means whatever is the current flowing here, whatever the potential difference was here, that potential difference, right, this potential difference is being, because there is no current flowing in this, that means that potential difference is being balanced by this EMF E. So that's why we'll say that this E is equals to VAJ, and that is equals to X into L, where L is the balancing length and X is the potential gradient. So if X is potential gradient, that is nothing but V by L, and this is the small l, that is the balancing length. And V is what? V is I into R, where R is the total resistance of the potentiometer wire divided by L into small l, where small l is the balancing length. And then coming to I, what is I? I is the current in the primary circuit, so that is nothing but E, that is the driver EMF, divided by R plus RH plus internal resistance of the battery, this into R by L, that is resistance per unit length of the wire, into L. So this is our EMF of the cell. The unknown EMF is this, right? So this is how we find the unknown resistance of the unknown EMF of the cell, that is by this formula. Or you can say this is the principle of the potentiometer circuit. Now out of this, E is known, R, that is resistance per unit length, will be known, balancing length we will be calculating, and at that point we will be knowing what is the resistance of the wire, what is the rheostat value, and what is the EMF, internal resistance of the cell. So this is about the potentiometer. The process of determining potential gradient is known as standardization of potentiometer. So this, what we are finding here, right, the potential gradient X is equals to V by L. This process of finding this is called standardization of potentiometer. So how do we do that? We let the balancing and length for the standard EMF E naught, and let that be equals to L naught, and then by principle of potentiometer we say that E naught is equals to X into L naught. So X is equals to that E naught divided by L0. That is how we find that. And this is the principle of the potentiometer or the device. Okay, so next we'll see application of this potentiometer. How are we going to calculate the unknown EMF E? I mean, we have the formula, but how we are going to use it in the lab, and how we are going to use it to compare EMF of two cells. So these two things we'll see in the next class, which I'll start in 2 minutes. So I'll stop this session now and we'll start the new session in 2 minutes.